In this video, I'm going to be repairing this M1 Apple MacBook Air, which I recently purchased off eBay. Now, this machine I bought because it was extremely cheap, at less than $100 is what I paid for this system, which for any Apple Silicon Mac really is quite a good deal. However, this machine has quite a number of issues that may or may not make that purchase worthwhile. We'll definitely see here in a minute. But straight off the bat, one of the major issues of this machine, which I try to avoid when buying these off eBay, but sometimes it can be a little bit difficult, is the screen itself is unfortunately damaged. Now, of course, there's nothing you can do to repair an LCD panel, so that, of course, has to be replaced, and is probably going to be the most costly part of this entire repair. Now, I will get into the further issues that this machine has in just a minute here, but otherwise, other than that cracked screen, the condition of the machine is pretty good. You can see we've got a little bit of a dent here, which is probably why the screen is damaged, because the screen in that corner is also damaged. But otherwise, cosmetically, it's in really good condition. Now, with that out of the way, let's go ahead and flip the machine over, and I will show you the major issue on the board that this machine has. So, taking a look at the board here, you can see the vast majority of it looks pretty much untouched. However, the obvious damage is, of course, the drilled NANDs, as you can see right here. Now, obviously, the main reason somebody might do such a thing is to ensure all data on the machine is destroyed. And, of course, drilling the NANDs will do that. However, my worry here is that the actual drill holes are so deep that they're actually drilling into the board as well. And if we go ahead and take an even closer look at them here, you can see that those holes are indeed quite deep. So let's go ahead and get a better view of them here. So yeah, you can see the holes are pretty deep here, and I'm afraid that this copper that you can see in there is actually inner layers of the board because they drilled so far into these NANDs. Now, I do have a solution to that. It's not a very easy solution, but if need be, we will be doing that in this video. Now, of course, the simplest solution to this issue would be to hopefully not have holes drilled through the board and be able to just remove and replace these drilled NAND chips. But I have a strong feeling that that is not going to be the case. So in addition to that, there are a few other issues, not with the board itself, but with other components in this particular chassis. So first, if we go ahead and take a look over here, you can see that somebody has completely torn the USB-C connectors just straight off here. You can also see that somebody has ripped this little microphone cable that plugs into here, and then someone removed the cable that sort of runs underneath the heatsink here and goes over to this board right here. You can see that cable is simply not present right there. So I don't really know what went on with this. I don't know if they just like forcibly tried to remove the board and just ripped all these ribbon cables like this. But the screen one is still intact. And they left some of these covers removed. So there's supposed to be one here covering these IPEX connectors for the antenna. And then there's also supposed to be one here to hold this connector in place. But they left this one, and then they left the one for that ribbon cable and other connectors over here. So just a little bit of an odd situation with this machine all around, but again, for the price I paid, I think it is still going to be worth it. So before we begin any of the repairs here, I first want to show you a new tool I recently acquired that should greatly assist in performing repairs such as this, and that is this Topdon TC002 lightning connected thermal camera. Now, Topdon is actually sponsoring today's video and sent me this device for use in board repairs such as this. Now, a thermal camera greatly helps in board repair as it allows you to very easily pinpoint shorted components on various boards. Now, I have used this for many repairs already, and as you can see here in this example, I was able to use it to find a shorted capacitor on a M1 Pro 14-inch MacBook Pro logic board that I recently had in for repair. And as you can see, as soon as I injected voltage into that board on that shorted rail, that capacitor was immediately visible on this camera. Now they do have quite a few different models of this. They do have a standalone one with a built-in screen. They have one for USB-C iPhones, and they have one for Android phones as well. So if you need a thermal camera, this is definitely a good and fairly cost-effective option. So I will put links to purchase these devices down in the video description, and I want to give a huge thanks to Topdon for sponsoring this video and sending me this thermal camera, which is actually something I've wanted for a very long time. So with that, let's get back to the repair. Alright, so as you can see here, I've got the board out and I'm ready to begin working on it. So of course, the first thing I want to do is just get these NANDs off and then just inspect the board in this area, see if the holes actually did get drilled into the board as I suspect. And in theory, hopefully if they didn't, we can just install new NANDs and be good to go. Alright, so as with any other NAND removal, the first thing we need to do is of course get rid of the underfill. And I'm not going to go into super in-depth detail on this particular video, but if you do want to see this process in more detail, I will put a link to my NAND upgrading video in the description below, so you can take a look at that and see the process in full detail. But for now, we're just going to get this nice and hot so we can remove the underfill. And with the underfill removed, we'll go ahead and just remove both NANDs. So just looking at it here, you can definitely tell they did get through the chips. You can see there's a nice big old hole in that one. And then this one's got 2 holes in it right there, straight through. So it did definitely hit the board, very slightly though, not as much as I thought. So I'm going to go ahead and just clean all this underfill off of here. We'll take a close look at it and see if we might actually be able to use this board here. So let's go ahead and get that underfill cleaned and pretty much just hope for the best here. Alright, so as you can see here, I've finished cleaning all the underfill off, and unfortunately it is not looking good. So you can see the worst damage is right here. That took out a good number of pads right here. Definitely went many layers deep into the board as well, probably causing shorts. And I did also look at the schematic, and some of the pads here are important. So unfortunately, I don't think this board is going to be usable. But as you can see here, this one is not quite as bad. This one is very minimal. If it was just something like this, it probably would still work. But this one is the real killer here. This one is going to make this completely unusable, unfortunately. So now we have to transition to plan B, and that is what I like to call a full board swap. And when I say full board swap, I don't mean just simply swap the board in this chassis with another one. I mean take a complete other system that's iCloud locked in the case of this one, and take the SoC on this one, which is not iCloud locked, along with all of its paired components, and solder them onto this board. Therefore, basically making this board the host for this machine, because of course the machine is determined by the ECID of the SoC itself. So in order to do that, it's a quite complicated process. We have to take this SoC off the board, reball it, and solder it onto this board, which sounds easy in practice, but it is actually quite a bit difficult to reball these specific SoCs. I've actually got another one right here, and as you can see, the pin pitch and the pad diameter here is extremely small, which makes it a little bit difficult. But I have done so many times, and I think I should be able to do it no issue in this instance. So to begin that process, first we need to get this board on the board preheater and prepare to remove its original SoC. Alright, so I've got the board up on the preheater all warmed up here. So the first thing we need to do to remove this SoC is to first remove this edge bonding on either side of it. So that's just done now that it's hot using a pair of tweezers. that should be good right there. So now we just need to apply some flux. And then we can use the hot air to heat and remove the chip. Alright, and as you see there, the chip has been successfully removed. So, now all we need to do is begin the reballing process. Alright, so in order to begin the reballing process here, of course, the first thing we need to do is clean off all the residual solder. Actually, before I do that, I'm going to tape it down using some Topdon tape. I'm just going to tape the chip down just like so. And now we can apply some flux and begin removing the solder. And with the vast majority of the solder cleaned off there, we're going to go and get the remainder off with some solder wick. Okay, and with that done, we just need to clean off all the old flux using some rubbing alcohol and a paper towel. And now that that's done, you can see the chip is now perfectly clean and it is now ready to be reballed. So now the next step is to get this chip inserted into the stencil and jig, and then we can begin reballing it using solder paste. Alright, so now with the jig in position here, I've actually got it on top of another jig, just the magnetic base of it, and that's because this magnet, it was really bad, it was really weak, and then it just fell out. It came, unglued from this, but I find just setting this on top of this one actually works really well. So now what we need to do is get the actual stencil itself, which looks like this, and then we need to position the chip appropriately, just like so, and then we just take the stencil and align it to the pads. There's no debris on there, of course. And that looks really good right there. Now, when you reball something like this, you got to be very careful of what solder paste you use. You do not want solder paste that is too liquidy. And this particular solder paste I have here it's okay. I haven't really been able to find the optimal solder paste to do this with. So sometimes it does take me a couple tries to get this right. But hopefully this time it'll go smoothly the first time. So what I'm going to do first actually is squirt a little bit of this out, because sometimes it's a little liquidy when it first comes out. This time it wasn't, but that's all good now. So now we're just going to squirt some on this stencil and then spread it around with a spreading tool. So that's about good there. And yeah, I can already tell it is a little more liquidy than I would prefer, but with this specific paste, it kind of boils off pretty quickly. The flux in this solder paste does, so it's usually not too much of an issue doing this. So with it on there, we just go ahead and take this spreading tool here and just push it down into the holes. Alright, and that looks really good and even. You want this to be obviously as even as possible. Now when I heat this, I tend to actually use the BGA nozzle that I used to actually remove the chip from the board initially. And that's because if you use a smaller nozzle, it actually will cause the stencil to start to warp, and then that will cause this solder paste to kind of just run all under it and make a huge mess, which of course we don't want. So I'm going to get that BGA nozzle ready to go here, and then we'll just begin heating this stencil and this whole jig assembly all at once, and that will ensure that it all heats evenly and there's no warping of the stencil. So this does take quite some time to do because this whole jig assembly and everything has a lot of thermal mass. So I do turn the air temperature up quite a bit to around 380 degrees Celsius, which is of course pretty warm for something like this, but it is what I find to be most optimal for doing it this way. And then you just kind of get it in position there and just hold it. And I try to heat it pretty slowly, start, you know, a little raised up and then get a little closer as we go on. And that way it'll boil off all this flux in the solder paste and make it less likely to run under the stencil and cause problems. Okay, and as you can see, the stencil did warp slightly, which I was not expecting, but I think it did it late enough after the solder had already melted that it actually didn't cause any problems. And make sure it's cool. Actually, I'll go ahead and just pull this off. Lift that off of there. And yeah, that's actually looking really, really good. Okay, sweet. That's what I want to see there. Let's take it off and just place it here. And then once my hot air cools down, I'm going to put some flux on this and we'll heat it a second time just to ensure all the balls have seated onto their pads. Alright, so everything's decently cooled down now and I've got the hot air nozzle removed. So I'm going to apply a little bit of flux here. Don't need too much on there. And then I'm going to take the hot air just with no nozzle on it and heat the chip like this. And there we go. That looks actually really good. It's not perfect. It's not 100% perfect, but it is pretty darn good. You can see in the middle here, you might not even be able to tell. It's very, very slight, but some of the solder balls are slightly different sizes than others in that area. But I've seen a lot worse than this work, so I'm pretty sure that this will work without any issues at all. So with that all done and reballed successfully, we can get the good board on the preheater and begin removing the SoC from there. Alright, so as you can see here, I've got the board all prepared and ready to remove its SoC. I went ahead and cleaned off all the underfill from the NAND pads here as well. But one thing I want to do actually before I start removing and replacing this SoC is I want to swap over the SEP or SEP EEPROM, and that is located right here. And as you can see, it's right on the back side of the SoC itself, and I don't want to risk having the SoC with its leaded solder fall off or something when I'm trying to replace this. So I'm going to go ahead and do it now before I swap the SoC onto this board. So this is the new board, which we have to remove this SoC, which is iCloud locked, and replace it with the new one. And then the SEP EEPROM is, of course, located right there. So I'm going to go ahead and remove the one from the original board that I took the SoC off of and solder it onto that board. So in order to do that, I'm just going to put it on the board preheater here. And I should also mention that this SEP EEPROM is one of the two components that we have to transfer from this board to the other one. The other component being the Wi-Fi chip, as that's paired to the SoC as well. But like I said, we're just going to do the SEP EEPROM for right now. And there's that removed. And now we just need to swap it out on this board. And there we go, the SEP EEPROM has been successfully swapped. So now we can begin the process of swapping the SoC. Alright, and now with the board fully up to temperature, the process will just be exactly what it was with the other board. Alright, and now with the chip successfully removed, we just have to clean these pads. And now with that done, we just have to clean it with some rubbing alcohol and a paper towel. Alright, and that's looking really good. So now we just need to apply some extra flux, or some new flux rather. And you don't want a whole ton on there, so I'm going to wipe a little bit of it off. Just like that'll be good. And now we just need to take our newly reballed SoC and align it into position. Alright, and that's looking pretty well aligned there. It doesn't have to be 100% perfect, but when you get down to ball size and pitch of this small size, you definitely want to get it really, really close. And I think I've got it. Luckily, it goes to the edge of the chip, which makes it a little bit easier to visually see whether or not it's aligned. But I've checked it over. I think it's good. So now we'll just heat it once again to solder it into position. Alright, and that looks like it's successfully soldered. You can see the, or you may have been able to see the chip slightly drop and the shimmer of the solder balls disappear when it did. And that is exactly what you want to see. So now we'll turn off the hot air and let the chip cool down, and then we'll take a close look at it and make sure it's soldered successfully. Alright, so everything's all done and cooled down here, so now we can go ahead and take a nice close look at this SoC here to make sure it's soldered successfully. So if we go ahead and take a look at the side here, you can see all those solder balls look perfectly even and all attached to the board. This is of course leaded solder. The solder paste I used was of course leaded solder paste, so that makes this process way easier than if I was using some sort of lead-free solder paste. But yep, that side looks good as well. We might be able to take a look at this side. Yep, that all looks good. Everything looks even. So that looks to be soldered on perfectly, which is exactly what I want to see. So now what I want to do is a preliminary test. So I'm going to put this board in the chassis, that rose gold MacBook Air chassis that it came from. We'll plug it into power and see if it boots into DFU mode. That should work just fine with the NANDs removed. And since the SOC EEPROM, this NOR EEPROM right here, has LLB and stuff signed for the original SoC that was on this board, it should just boot straight into DFU mode without needing to use any jumper or anything. So with that, let's get this installed and give it a preliminary test. Alright, so as you can see here, I've got the board installed. I've also got a second M1 MacBook Air sitting right over there so we can check the status. So now we'll go ahead and connect power to the board. So what you want to see when you connect power with one of these ammeters is it should stay at 5 volts and pull about 100 milliamps or so. So let me position it so you will be able to see that without issue. And go ahead and plug it in. Okay, that's a good sign so far. And you can see we're pulling about 0.07 amps or 70 milliamps or so, which is fine. So now we'll go ahead and plug the USB-C cable into the DFU port. And yes, as you can see there, the machine has been successfully detected in DFU mode. And if we go ahead into Finder, you can see it is showing up right there. So that is perfect. So now all we need to do is finish installing the rest of the components. So we need to install some NANDs onto this board, and then we need to transfer the Wi-Fi chip from the original board to this board, And then we can try to restore software onto it and make sure it fully works. So with that, we'll go ahead and first start by swapping the Wi-Fi chip. Alright, so in order to begin the Wi-Fi chip swapping process, of course, the first thing we need to do is remove the donor or the correct Wi-Fi chip from the original board. So I've got that right here, and that process will be exactly the same as removing underfilled NANDs. So I'll go ahead and start doing that now. And just like that, the Wi-Fi chip has been successfully removed. So now what we need to do is actually clean all the underfill off the chip itself. Alright, so in order to clean this chip off, I've got the hot air propped up in the BGA stand that I usually use. And that way I can use both hands, one to hold it with tweezers and the other to scrape on it with the underfill tool. So let's get the hot air warmed up again and scrape off all that underfill. Alright, so with all the underfill removed, now we just need to remove the residual solder using some solder wick and soldering iron. And with that done, we can now begin reballing the chip. Alright, so in order to reball this chip, I'm just going to use this stencil right here. I'm just going to take some Topdon tape and place the chip on it like so, and then put it in position on the stencil. Just like so. You can see all the pads line up with the holes on the stencil perfectly. So with that done, we just simply need to apply some solder paste. So now that the solder paste has been applied, we simply need to heat it with hot air to melt the solder paste onto the pads. And I'm going to use a pair of tweezers here to kind of hold it against the chip so it doesn't lift or warp or anything. Yeah, so there's a little bit of an example of what happens when the solder paste is too liquidy. As you can see, it kind of made a little bit of a mess there. So I will have to do this one more time. So I'll go ahead and do that off camera, and we'll begin the process of installation once that's done. Alright, so after attempting to reball it a second time, as you can see, this time it looks absolutely perfect. You can see all the balls are uniform on their pads, and there's nothing that looks out of the ordinary there. So I'll go ahead and set that aside, and now we just need to remove the Wi-Fi chip from this board. And with the chip removed, now we need to remove all the residual underfill. And now with all the underfill removed, we can apply some flux and clean off all the residual solder. And with that all clean, I'm going to get this in the small board preheater, and then from there we'll solder on our newly reballed Wi-Fi chip. Alright, so with the board on the board preheater here, now we can simply apply a little bit of flux. Just like so, and then take our reballed Wi-Fi chip and place it into position. Alright, and that looks pretty well aligned, so now we'll just heat it with the hot air to solder it on. And that looks good right there. So now with that installed, the next step, of course, is getting some NANDs installed on this board, and then we can finally give it a full test. So let's get started with that now. Alright, so in order to begin here, the first thing we need to do, of course, is prepare the NANDs to install on the board, and like we did with the Wi-Fi chip, we simply need to reball them with a stencil. Now, these NANDs I've got right here are a 512 gig set, as you can see right there, and these are actually the original NANDs from that rose gold MacBook Air, the board we've been soldering these components onto. So I'm just going to reball these and solder them right back onto that board. So let's just get started with that now. Alright, so as you can see here, both NANDs have been successfully reballed. So before installing them on the board, the first thing we need to do is apply some flux, just like always. So let's go ahead and do that. And with the flux applied, because these are programmed NANDs, these are actually from this exact board as I mentioned, they do have to go back in their exact same positions. So on the M1 MacBook Air, this position is position 1, or position 0 rather, and this one is position 1. So the one I have labeled 0 has to go on these pads right there, and the one I have labeled 1 has to go right here. So yeah, that looks about good there. So now we'll just take the hot air and solder them into position. And just like that, both NANDs are now soldered on successfully. So that should be every component that we need to transfer from the original board to this board. So now, in effect, we should have sort of a combination of both of those boards, you know, with all the paired components for this specific SoC, but with the NANDs of the donor board here, so the NANDs that originally came off of this machine, which will give us 512 gigabytes of storage. Now, I could have upgraded this to 1 or 2 terabytes if I wanted to, but for this specific machine, I really don't need that, and since I had the 512 gigs that I had already taken off of this board to begin with, I may as well just use those chips. So with that, let me go ahead and get a heatsink installed onto this board. We'll get it reinstalled into the chassis once again, and then we'll finally be able to attempt a DFU restore. Alright, so as you can see here, I've got the heatsink installed on the board, and I've got the board mostly installed in the chassis here, just with a couple screws to hold it in. And I've got the USB-C ammeter plugged in once again, as you can see right here. So in theory, once we plug it in, it should go straight into DFU mode like it did before. And yep, as you can see there, about 0.07 amps, which is exactly what I want to see. So yeah, it's definitely in DFU mode and ready to be restored. Now before I do that, I'm going to go ahead and just plug the battery in it here, just to have that in. There we go, battery is connected. So now I'm going to go ahead and get the bottom cover placed in place, just so we don't have to, you know, let the board touch all this underfill and solder we've got on the table here. So we'll go ahead and just put that down here. Open it up, and then I've got the USB-C cable connected to that other MacBook Air as I showed you before. So we'll go ahead and plug that into the DFU port there. And sure enough, on the other machine, it detects the machine in DFU mode. So with that all set up there, now the only thing left to do is attempt to perform a DFU restore. Let's go ahead and select an IPSW here. We'll go ahead and install 15.1 Sequoia and attempt to restore the device. Okay, we're in recovery mode, that's good. Alright, we're looking pretty good so far. We've got an Apple logo on the screen, as you can see there. And we are now restoring, or at least in restore mode. And yep, we've got a increasing progress bar on the MacBook Air here. So that means everything is working. So yep, there it goes. It's successfully restoring. So now we just need to sit here and wait for the restore process to complete. Alright, so as you can see here, the restore process is almost complete, so it should reboot any minute now. And there it goes, the restore has completed successfully. Let's go ahead and unplug the USB-C and wait for it to reboot. And there it is. And just like that, we're at the first time setup. So let me go ahead and get this machine all set up, and we'll take a look at the final results. And just like that, the machine has been set up successfully. So as you can see, it's fully in the OS. It's not iCloud locked, which is what I expected. And I only knew that by checking the serial number on that actual original M1 MacBook Air chassis. So I'm pretty glad that at least the board that was in that machine was the original one for it. So everything seems to work. I've gone through and tested everything. The battery works, Wi-Fi works, as I'll show you right here. You can see I've got that connected and everything working there. So the only thing I have left to do on this machine is I need to transfer the Touch ID sensor right here with the one from that original chassis that the SoC came from. And the reason for that is, of course, the Touch ID sensor, like all those other components that we had to transfer on the board, is also paired to the SoC itself. So once we transfer that, Touch ID will work as well, but as it is, everything else works as expected. So with that, let's go ahead and check out about this Mac. So you can see there that this is a base model M1 MacBook Air, and that's about what I expected with this. You know, I couldn't really expect, any upgrades with a very cheap MacBook Air I bought off eBay. But despite that, I am still very satisfied with the results here. So we go ahead and go into more info. You can see that, yep, there is the 512 gig SSD with those NANDs that we installed, which, like I said, were actually the original NANDs from this rose gold MacBook Air board. So that's good to see there. And if we go to NVMe Express, you can see it's detected as the AP0512Q SSD right there. So memory, we've got 8 gigs of LPDDR4 manufactured by Hynix on this particular SoC, and I think the original one that unfortunately was iCloud locked, as I mentioned, but I think the SoC that was originally part of this board was a upgraded 16 gig RAM model. So it's a bit of a shame that I lost that in this instance, but again, it's iCloud locked. There's nothing I can really do otherwise. So the GPU, 7-core GPU here, like I said, just base model specs there. So that has been the successful repair of this extremely cheap M1 MacBook Air, or technically I guess the combination of two M1 MacBook Airs. This rose gold one I actually got for free, so I didn't spend any extra money there. But that has been the combination of two M1 MacBook Airs to make one fully functional machine for very little money. So with that, I hope you enjoyed this video.